Okay, so we're going to be talking about two-factor ANOVAs. This is section 4 and section 5 from chapter 13, which you can find in your textbook. It's pretty clearly labeled. We're going to skip over the repeated measures ANOVA, which is sections 1 through 3. So before we get to the two-way ANOVA, let's do a few learning check questions for the one-way ANOVA that we talked about in chapter 12. A one-way ANOVA produces sum of squares total that equals 80 and sum of squares within it equals 30. For this analysis, what is the sum of squares for between groups? And here are your choices. I'll give you just a minute to try to answer this one on your own. My answer is 50, right? Because sum of squares total equals sum of squares within plus sum of squares between. So 50 and 30 equals 80. Okay, next one. Which combination of factors is most likely to produce a large value for the F ratio? Again, I'll give you a minute to look through these choices and see if you can choose the correct answer. Okay, and the answer here is B, large mean differences and small sample variances. So if the F ratio is between groups variance over within group variance, right? And so if you have large mean differences between the different group means, and small sample variances, meaning a small within group variance, that's going to give you the largest F ratio value. And if on any of these questions, if you have watched the chapter 12 lecture and looked at the textbook and you still are not getting these answers or you don't understand where they're coming from, a good time to go back and review or watch the lecture again or send me an email, okay? Okay, I think one or two more. True or false, post hoc tests are needed if the decision from an analysis of variance is fail to reject the null hypothesis. So you do an ANOVA, you decide that you're not going to reject the null. Would you then do post hoc tests? The answer here should be false, right? So post hoc tests are only things that you do if you reject the null. So recall when you're doing an ANOVA, rejecting the null hypothesis means that there's at least one mean that is different from another. And we don't know from the ANOVA itself which one is different from another, but we know that there's at least one difference that's significant. And that's when you would need to do post hoc tests to figure out which one or which ones are different from the others. If you have failed to reject the null hypothesis, indicating that there are no means that are different from another, then you don't need to do any further analysis because there's nothing else to figure out. Hopefully that makes sense. Okay, true, false. A report shows these ANOVA results. So an F value of 5.36 when you've got degrees of freedom of 2 and 27, and a p-value of less than 0.05. You can conclude that the study used a total of 30 participants. True or false? So I'll give you a hint. You're going to want to be looking at those 2 degrees of freedom values. The answer is true. So when you have the degrees of freedom values, you can figure out how many total participants were in the study. So this is a repeat of a question and answer that we looked at in the chapter 12 lecture. The formula for the first degrees of freedom is k minus 1. And just doing some basic backwards algebra here, if k minus 1 equals 2, then k must be equal to 3. And here's a formula for the second degrees of freedom that's reported. N minus k equals 27. Again, just doing some basic algebra here, plugging in 3 for the k and 27 for the degrees of freedom, you would get n equals 30. And so that's correct. When the degrees of freedom reported are 2 and 27, the n value, or total number of participants in the study, is 30. Okay, so moving on to two-factor ANOVAs, chapter 13, sections 3 and 4, or excuse me, this should be 4 and 5. I apologize that this slide is incorrect. Up here it should say 13.4 and 13.5. We should be able to understand a two-factor study and something that we're going to look at called a matrix of group means. Very exciting. Describe main effects and interactions, and we'll talk about what interactions are. Compute a two-factor ANOVA, evaluate the means for a two-factor independent measures study, measure effect size, interpret results, and articulate assumptions. So we'll be able to do all kinds of things when we're done here. So, factorial designs. So all of the statistical tests that we have done so far have involved just one independent variable. So we've examined how groups differ across different levels of a single factor, right? We've looked at like the levels of a single factor of treatment type, right? Art therapy and play therapy and cognitive behavioral therapy, for example. Here's another one. Do pre-treatment levels of stress impact depression scores? And the levels of stress could maybe be low, medium, and high. And for that, would we use an ANOVA or a t-test? And just to review, we would use an ANOVA, right? Because a t-test compares two group means, and ANOVA is what you would use if you have more than two group means, right? So ANOVA is you have more than two group means that you're trying to compare. Maybe you have 3 or 4, and you don't want to do 3 or 4 t-tests because that would inflate your probability of making a type 1 error. And so you would use an ANOVA. But you'll notice that both of these examples I've given you are looking at one independent variable, right? Maybe treatment type, maybe levels of stress as the independent variable. And even if there are 2 levels or 3 levels or 4 levels, there's still just one variable. Here's another example. Does political affiliation affect negative emotion recognition? So you might, here our independent variable or factor is political affiliation. And we've got 2 levels of that factor, Democrat and Republican. And we're looking at whether or not being a Democrat or Republican affects negative emotions. For this one, what would you use, ANOVA or t-test? And the answer would be t-test because there's just 2 levels, right? You can do a t-test when you've got 2 means that you're trying to compare. But again, you'll notice all of these examples just have one independent variable. The problem with that is that in psychology, we often want to conduct studies that have more than one factor or more than one independent variable. And those types of studies that have more than one independent variable are going to use something called a factorial design. And a factorial design is used for an experiment or study that has 2 or more independent variables. And we can do that, we can examine or investigate many independent variables at one time using ANOVA. It's a different kind of ANOVA, but it's still the very same concepts that we've been talking about. And we're only, for this lecture and for this class, we're only going to worry about factorial designs with independent samples, not repeated measures. So the beginning of chapter 13 talks about repeated measures designs, ANOVA designs. And just so you understand, repeated measures would be when you're using the same group of participants. Maybe you're looking at them before and after treatment, or at 3 different time points, right? Before treatment, after a week of treatment, and after 6 months of treatment. Or you're having the same participants go through 3 different treatment conditions or levels. Those would be repeated measures designs, and we're not going to talk about those. We're going to be dealing with independent samples, meaning that there's a separate group of participants for each level and each level of the independent variables. So ANOVA, factorial ANOVAs are labeled a particular way, and I'm going to try to go over this quickly, but basically the format for naming or notating a factorial ANOVA is right here in the second bullet. The number of levels, number of levels for factor A by, you say, when you see the X, instead of saying times, you say by the number of levels for factor B and the number of levels for factor C by the number of levels, et cetera, et cetera. And so you can have an infinite number of factors. A factorial ANOVA, again, is 2 or more independent variables. Up to this point, we've been just looking at one independent variable at a time. The number of numbers tells you how many factors or independent variables are being examined. And the actual numbers tell you how many levels were in that independent variable. So I'm going to skip here down to this example. So if, let's say, we have a 3x2 ANOVA, what do those numbers mean? Because there are 2 numbers, right? There's a 3 and a 2. We know that there are 2 independent variables because the number of numbers tell you how many factors or IVs are examined. So here we've got 2 different numbers, a 3 and a 2. If this was a 4 and a 3, or a 2 and a 2, or a 3 and a 6, as long as there's 2 numbers, then you know there are 2 independent variables. The other thing we can know about this notation is that factor A, or the first independent variable, has 3 levels, and factor B, or the other independent variable, has 2 levels. And so this goes to this point here. The actual numbers tell you how many levels were in the independent variable. So this number tells you how many levels of the one independent variable, and the 2 tells you how many levels of the other independent variable. And then if you multiply the numbers together, you can learn or know how many total groups there were. So in this 3x2 example, we know that there are 3 times 2 is 6, 6 total independent groups. That means there were 6 total independent groups of participants measured or assessed in this study. So let's do a couple of questions to make sure we've got this down. How many factors and groups would a 2x2x2 ANOVA have? So how many factors and how many total groups? Remember, the number of numbers tells you how many factors there are. And then if you multiply the numbers together, you can learn how many total groups there are. So the answer here is C. There are 3 factors because there are 3 numbers, right? 1, 2, a second 2, and a third 2. So there are 3 numbers in this study. That means there are 3 factors. And if you multiply 2 times 2, you get 4. 4 times 2 is 8. So there's going to be 8 total groups in this ANOVA design. So make sure you understand the notation. Here is an example of a 2-factor factorial design. So a 2-factor factorial design would have 2 numbers, right? And depending on how many levels are in each factor, that would tell us what the 2 numbers are, okay? So for this example, a researcher is interested in studying the effects of audience pressure and self-esteem on exam performance. All participants took an exam. The researcher had half of participants work alone, meaning there was no audience, and half of the participants work with an audience of people claiming to be interested in observing their test-taking behaviors. So a group of people watching you take a test, right? And then the researcher also divided people up into 2 groups based on personality, those that are high in self-esteem and those that are low in self-esteem. And the dependent variable in this study was the number of errors made on the test. So here is a matrix which describes or shows what this study is going to look like. Across the top, we have, and let me go across the side here first. Factor A, self-esteem, low or high. So the top row are going to be low, participants with low self-esteem, and the bottom row are going to be participants with high self-esteem. And then across the top, you see factor B is the audience condition. And remember, that's either no audience or an audience. And you'll see this is a 2-by-2 factorial design, like this says down here, because there are 2 independent variables and each one has 2 levels. This is going to be called a 2-by-2 factorial ANOVA, right? So here's one independent variable, self-esteem. Here's another, audience condition. So we know there's going to be 2 numbers. Because self-esteem has 2 levels, low and high, and audience condition has 2 levels, no audience or audience, then each of those 2 numbers is going to be a 2. So this is a 2-by-2 factorial design. And a 2-by-2, if you multiply 2 times 2, you get 4. And you'll see that's exactly how many boxes we have here. So we're going to have 4 independent groups of participants. This top left box, just as an example, this is going to be the group of participants who have low self-esteem and no audience while they're taking their exam. We'll look at the bottom right box. This is going to be participants who are classified as having high self-esteem and are tested with an audience. And again, we're not looking at repeated measures for this chapter or lecture or in this class. So each of these boxes represents a separate independent group of participants, right? We're not going to have participants take an exam twice, once with no audience and once with an audience. That is not what we are doing. Here we're going to have a group of participants that have low self-esteem and are tested one time only on the dependent variable with no audience or with an audience, right? So independent measures, factorial design. Okay. Some questions we might want to ask from the example study. So what happened to the mean number of errors or the average number of errors when the audience is added or taken away? So these are some things that we might be interested in asking and that we could find the answer to with a study like this, a 2-factor factorial design. One thing we might ask is, what effect does the audience have? So if people are watching you take an exam, what does that do to the number of errors, right? And you might guess, like, I bet having an audience or someone watching you take an exam might increase the number of errors on the test. And this would be a question about the main effect of factor A, right? So you'll notice in this question, we haven't mentioned self-esteem at all. We haven't said high, low, or otherwise. We haven't said anything about self-esteem. We're just simply asking, what happens to the errors when you have an audience or don't have an audience? So that's just a main effect of one factor. You might also ask, is there a difference in the errors if you have high or low self-esteem, right? Like, what effect does self-esteem have on errors just by itself? Again, you'll notice in this question, it doesn't mention the audience at all. It's not even a factor in this question. And this would be a question about the main effect of factor B, or self-esteem, right? So all by itself, does having low or high self-esteem have any effect on your test, the score, and the number of errors you make? And then a third question you might be wanting to ask, and you'd be able to ask with this kind of design, is how do specific combinations of self-esteem and audience together affect performance? So another way of saying that is, does the presence of an audience impact the number of errors more for people that have low self-esteem? So let's say you come in to take a test, you've already got low self-esteem when you walk in the door, right? And then there's an audience of people watching you. Maybe um, low self-esteem folks are going to do worse on the exam than the high self-esteem folks, especially if there's an audience watching them, right? And maybe the high self-esteem people, they walk in the door, they've got high self-esteem to begin with. Having an audience maybe affects their scores a little bit, but not much, right? They have a high self-esteem, maybe that's kind of a protective factor. And so the audience affects their scores just slightly, but not too much. Where the low self-esteem people, having an audience really affects their scores. Maybe it cuts it in half. And so this kind of question or consideration is called an interaction effect. We're asking about, how does one factor influence another? How does self-esteem influence the presence of an audience or not, with regard to the number of errors that are made on an exam? So we'll talk a little bit more about main effects and interactions in a later slide, but you might want to review these terms in your textbook and make sure you really grasp what a main effect and an interaction is and how those are different. So when we only had one factor or one independent variable, we only needed one F ratio to represent the effect of that factor, right? So we looked at different kinds of treatment, for example, right? Art therapy, play therapy, cognitive behavioral therapy. And we just needed to compute one F ratio in our one factor ANOVA to figure out what's the effect between the different levels of that factor, right? So we had between subjects. Now, with this two-factor ANOVA, we're going to end up computing three different F ratios for the three different hypothesis tests that answer those three questions. And what are those three questions I'm referring to? Back to this slide, right? The main effect of factor A, the main effect of factor B, and the interaction between the two. So those are three key questions, and we're going to compute an F ratio for each of those three questions. Recall that the F ratio, or the F test statistic, is the variance or differences between sample means divided by the variance or differences that you would expect with no treatment effect, right? So the numerator in the F ratio is the actual mean differences in the data. So what are the differences, the average differences in the sample data that you've got. And remember, that will include any treatment effect if there is one, uh, and it will also contain some random variance. And the denominator is going to be differences that would be expected if there is no treatment effect, right? If the null hypothesis is true. And so it's the differences that we would expect just due to sampling error or chance variability alone. No actual treatment effect difference. Okay, so how do we get these three different F ratios? We'll do the main effects F ratios first, okay? So the first main effect, do differences in self-esteem, that's factor A, result in differences in performance? Remember, main effects is just looking at one factor or independent variable at a time. So for this, we're going to compare the mean score for participants with low self-esteem and compare that with the mean score for participants with high self-esteem. And we're not going to pay any attention to audience, yes or no, right? So we're just going to add across, or not add across, but compute the averages across these two rows, low and high self-esteem. Low self-esteem, average number of errors is 8, and the high self-esteem, average numbers of errors is 4. So they're clearly different, right? They're like 4 points different. But are they different enough that they are unlikely to occur by chance? Right? And that's what we're asking with any of our hypothesis tests, right? T-tests or ANOVAs. We're looking at the differences between two or more means and trying to ask and answer, is this difference that we see due just to chance and sampling error, or are they meaningfully or significantly different? Again, main effects ignore the treatment differences caused by the other factor, right? So we're ignoring any differences that we see in the audience factor. And then the other main effect we're going to look at is main effect for factor B, which is the audience. Do differences in the audience condition result in differences in performance? So just like the self-esteem, we're going to compare the mean score for all participants with an audience in this column here, the first column, with an audience, or excuse me, with the mean score for those without an audience. Sorry, I've got this backwards here, right? I compare the mean score for all participants with an audience, that would be the second column. Compare that with the mean score for those without an audience, the first column here. We're going to collapse these values and not pay any attention to low and high self-esteem. So just calculating the means here, the mean number of errors with no audience is 5, and the mean number of errors with an audience is 7. So just like we did for self-esteem, you are calculating across or down the columns here to get the main effects for the factor of audience condition. And again, we do see a difference. It's a 2-point difference, right? Average of 5 versus an average of 7. But are those group means different enough that they're unlikely to occur by chance? That's the million-dollar question that we're going to need to answer. So again, we're so far just focusing on main effects, right? We're going to ask and compute 3 F ratio values, and the first 2 are main effects. So the null hypothesis would be that there are no differences in the mean number of errors between the 2 levels of self-esteem, right? The mean for low self-esteem equals the mean number of errors for high self-esteem. No effect. The alternate hypothesis would be that there is a difference in the mean number of errors between the two levels of self-esteem. So the mean for low self-esteem does not equal the mean for high self-esteem. And then the null hypothesis for the main effect of factor 2, there's no difference in the mean number of errors between the two levels of audience presence. So the mean of the first level of factor B, so B1, equals the mean of the second level of factor B. So in other words, the mean for no audience is the same as the mean for the presence of an audience. No difference between those two levels. And of course, the alternate hypothesis would be just the opposite, that there is a difference, that those means are not equal to each other. How do we evaluate these null and alternate hypotheses? We're going to calculate an F value. And just like the ANOVAs that we talked about in chapter 12, the F value is going to be the variance between sample means divided by variance expected with no treatment effect. So what would be the variance that you would expect if there's no treatment effect or no difference at all? What would you expect the variance to be if the null hypothesis is true? And you're going to do it twice. You're going to compute one F value for factor A and one F value for factor B. Okay, now let's talk about interaction effects, right? For the two-way factorial ANOVA, we also want to evaluate the effect that is due to the unique combination of the two factors. So interaction effects are a really unique feature of the two-way or factorial ANOVA, and it allows us to examine whether those two variables interact to produce unique effects. So remember our example, do specific combinations of self-esteem and audience presence acting together have effects that are different from the isolated effects or main effects of self-esteem or audience presence? So with interaction effects, you're kind of going beyond what's the effect of, self-esteem all by itself, and what's the effect of an audience presence all by itself. And then with an interaction effect, you're asking, when you put those two things together in different combinations, what goes on, right? It's above and beyond just the effects of self-esteem or audience by themselves. And this, you can kind of think of it like a drug interaction, right? A drug could have a positive effect for most people, right? In most cases, but in certain conditions or with certain people, maybe the drug could be deadly. Okay, so the main effect of the drug is good, it's maybe helpful, but the interaction of a particular drug with a particular condition is definitely not good, right? Or, another drug interaction example is two different drugs, right? Tylenol and aspirin by themselves both do certain things and are used to treat certain conditions. When you put them together, you get some special different kinds of effects than one or the other by itself. And so interaction effects are just exactly that. They are special effects or unique effects that go on when you put two variables together. Again, if this isn't making sense to you, go to your textbook and read. There's just a couple of pages about interaction effects, and it describes it in more detail if you're having trouble understanding this concept. So how do you find this interaction effect? How do we measure it in statistics? Again, we're going to look for any extra differences that are not explained by the main effects. And we're going to presume that those extra differences that we can't explain with the main effects are due to the interaction. So you can kind of guess, maybe mathematically, how we're going to get this or calculate these effects. So for our previous example, there are two main effects, but no interaction. So this is just an example. These are the same exact numbers that we were looking at when I was talking about main effects. And this would be an example of no interaction effects. And this is one outcome that's entirely possible when you're doing a two-way ANOVA or factorial ANOVA. Sometimes you'll see main effects, but you won't have any interaction effect. How can I tell that? So if you add an audience, so you'll see you get for low, let's look at just low self-esteem for a second. No audience, you have 7 errors on average. With an audience, 9 errors on average. So it went up by 2. If you look at high self-esteem, you get the same exact increase, right? They had 3 errors without an audience and 5 errors with an audience. So whether you have low or high self-esteem, adding an audience results in a 2-point average increase in the number of errors. So when a difference in one variable, audience, is the same across the levels of the other variable, there's no interaction effect. I'm going to show you another example, and this might become more clear. Here's an example with an interaction, and you'll notice the values inside the cells here in the center have changed. So I'm going to go back to the previous slide real quick here. Here's our main effects out here at the bottom of the columns and the very end of the rows. Remember, these were the values that we were looking at for main effects. And this is a different example, same main effects here, right? Low and high self-esteem, there's a 4-point difference in errors. Audience and no audience, there's a 2-point difference in errors. So the main effects are exactly the same, but I've changed the values in here. And this would be an example of finding a main or an interaction effect. So again, the main effects, which are measured with the values out here at the end of the rows and the bottom of the columns. And then how do we tell that there is an interaction? It looks like adding an audience results in a different increase for low self-esteem and high self-esteem groups. So look at this. When you have low self-esteem, adding an audience increases your errors on average by 4 points. So low self-esteem folks make an average of 6 errors just to begin with. Then you add an audience and all of a sudden they're making 10 errors. Contrast that with the high self-esteem people. They start out making 4 errors, so fewer than low self-esteem. But when you add an audience, it does absolutely nothing. They're still making, on average, 4 errors. So in this case, there's an interaction going on here. Having an audience does make a difference, but only for the low self-esteem group, not for the high self-esteem group. And this is, by definition, this is what an interaction is or what that looks like. And take note here, there are still 2 main effects present, right? There is a group mean difference for low and high self-esteem, and there's a mean difference for the audience and no audience groups. And there is an interaction. Now, if you do the math, all this math still works out. This is still the actual average for the no audience condition, for example. But if these were the results you had, you would be looking at an interaction effect as well as main effects. And there's our interaction in the body of the matrix. The effect, another way to say this, the effect of audience presence, factor A, depends on self-esteem, factor B. So, how do we state this null and alternate hypotheses for the interaction effects? The null hypothesis is just that there's no interaction between factors A and B. They do not influence each other. Factor A does not influence factor B. Another way to say that is that the effect of factor A does not depend on the level of factor B. Or the effect of factor B does not depend on the level of factor A. The mean differences between treatment conditions are explained by the main effects of the two factors. The alternate hypothesis is that there is an interaction between factors A and B, that the effect of one does depend on the level of the other. You could also say the mean differences between treatment conditions are not what would be predicted from the overall main effects of the two factors. So in other words, there's differences going on that are above and beyond what you'd expect from just main effects. How do you evaluate or calculate that with an F ratio? You're first going to identify mean differences that are not explained by main effects. And the extra mean differences are then evaluated by an F ratio. So the F ratio for interaction effects on the numerator, it's the variance or differences between sample means that are not explained by main effects. And then the denominator are, again, the variance expected with no treatment effect, right? And that's exactly the same as the last two F ratios, the main effect F ratios. Often, interaction effects are easiest to see with a graph. So you want to understand conceptually what's going on with interaction effects. But the quickest way to tell whether or not interaction effects exist or if they're present is to look at a graph. And you can spend some time on this slide. Feel free, of course, to pause the lecture here and really look at this for a little while and make sure that this makes sense to you, kind of talk it through. In the first example on the left, you see that each variable increases the number of errors, but they seem to do so independently, right? The low self-esteem line and the high self-esteem line are different, but the errors go up at the same rate for both the audience and the no audience groups. So what these two graphs are just the matrices we've been looking at in a graph form. Okay, so we took the two columns, audience and no audience, and put those on the x-axis, and then we put our dependent variable along the y-axis, so the number of errors, and then we used two different lines to represent the two levels of the other factor, self-esteem. Excuse me. So the number of errors for no audience and low self-esteem was 7, and no audience and high self-esteem, the errors are only 3. And then when you add an audience, in this case, so this is one data set, let's say, the errors go up when you add an audience for both the low self-esteem group and the high self-esteem group, but they do so at exactly the same rate, right? So it looks like they go up by 2 from 7 to 9 for low self-esteem, and they go up by 2 from 3 to 5 for high self-esteem. So on the left, if this data set is graphed, this is showing no interaction effect. Over here on the right, there's a clear interaction effect. So visually, you can see right away, right? These look different. This would be an interaction effect. This would not have an interaction effect. On the right, the low self-esteem group overall makes more errors, right? This bar is above this bar. But this time, when the audience is added, the effect is clearly greater on the low self-esteem group, right? So recall in my second example, let's say I was to do this experiment again and get a whole different set of data. Here, my high self-esteem folks scored 4 errors, whether there's an audience or no audience. Low self-esteem people scored more errors than the high self-esteem, but even greater difference when there's an audience present, right? And this is an interaction effect. So it says down here, lines would either cross, they do cross, or you could see that they would cross, right? If you continued the lines and you drew them out, you'd find that they would cross. Over here, they're parallel. So again, this is just an easy way to see immediately, quickly, whether there's an interaction effect or not. So what are the possible outcomes for a two-way ANOVA? There's actually many different possible outcomes. You may find that there are no main effects and no interaction effects. So you would fail to reject all the nulls, right? The null hypothesis that there's a main effect, don't fail to reject it. The null hypothesis that there's no interaction effect, fail to reject it. So you don't see any differences at all. Another possibility, one main effect and no interaction. So you might reject the null for factors A or B and fail to reject all the other null hypotheses. There might be one main effect and an interaction, where you would reject the null for one or the other factor and fail to reject the null, or that's incorrect. This should say reject the null and reject the null for the interaction. Sorry about that error. You could have two main effects and no interaction. You could have two main effects and an interaction. And in that case, you'd reject all the null hypotheses, right? Or you could have no main effects, but have an interaction effect. So in that case, you'd fail to reject the null hypothesis for factors A and B, the main effects there, but you would reject the null for the interaction effect. So as you can see, there are many, many different outcomes for the two-way ANOVA. A two-way ANOVA, you're going to have 3 different F ratios, and there's all different combinations of what you would do with the hypothesis test for each of those F ratios. And so what you should conclude from listing all of those possible outcomes is that all of the tests of main effect and interactions are independent, meaning you do not have to have main effects to have an interaction. You don't have to have an interaction to have main effects. So when you conduct a two-way ANOVA, you're essentially doing 3 separate hypothesis tests in one, and not even like in one computation. You're literally doing 3 different hypothesis tests. Okay. So the outcome for any of the 3 tests is unrelated completely to the outcome of either of the other 2 tests. So when we test to see main effect for factor B here, that has nothing to do with whether we find a main effect for factor A or not, and whether we find an interaction effect for the two interacting together. The outcome for each of those three tests is completely independent of the others. And this is an important concept, something really important for you to remember. And you might ask, okay, that all sounds good. They're totally independent. We're doing 3 different hypothesis tests. What about that type 1 error though, right? So if we're gonna have type 1 error and we're doing 3 different calculations, aren't we gonna end up with the inflated alpha or increased chance of committing a type 1 error? The answer is no, because each test is its own completely separate hypothesis test. So here we are kind of taking advantage of the fact that each of these 3 tests is completely independent of the others. And for that reason, we're not going to be inflating the alpha. When you're comparing 2 or more tests and they're not separate, then you could increase or inflate the alpha. Okay, sorry about that. I'm recording these lectures late at night after my 2 daughters are sleeping and one of them just woke up. So a little break in the action there. Let's see, let's keep going. Okay, so let's do a quick learning check. How many separate F ratios are used in a 2-factor ANOVA? 1 overall F ratio or 2, 3, or 4 separate ratios? I'll give you just a minute. Okay, so the answer is C, 3 separate F ratios. Remember, in a 2-factor ANOVA, there are 2 independent variables or 2 factors. And so there's 1 F ratio for the main effects of factor 1, another F ratio for the main effects of factor 2, and a third F ratio for interaction effects. Okay, so here is the basic structure of a 2-way ANOVA. So there's going to be 2 stages here. So just a little, like another layer or another additional stage than the ANOVA we did for chapter 12. So total variance, just like with ANOVA, one-way ANOVA, is going to be broken down into between treatment variance and within treatment variance, right? There's the variance that exists between one level and another, and then there's the variance within each level. And the within treatment variance is going to be the denominator for all 3 F ratios. Okay. And like I just said, within treatment's variance is the denominator, and that's because any within treatment variability cannot be caused by the treatment effects, right? So within a particular, if you had, let's say, 3 different types of treatment, within one type of treatment, any variance that exists due to something other than the treatment effect, right? The treatment effect just exists across the treatment types or levels. And then in stage 2, the between treatment variability gets partitioned into factor A variance, so differences attributed to factor A, differences attributed to factor B, and then any remaining differences that define the interaction. So these three values or components will become our numerators for the three different F ratios. So remember, we're going to compute for this two-way or two-factor ANOVA, we're going to compute three different F ratios. They're going to represent the main effects for A and B, and they're going to also represent the interaction effect, or testing for the existence of an interaction effect. So those are going to be the numerators, and then the denominator for all three, again, is the within treatment variance figure. So there are some similarities, right? Just like in the one-way ANOVA, the goal is to figure out how do we break down the variances. There are three between treatment variances. So factor A and B, and those are going to be main effects, and then the interaction between the two, the interaction between factor A and factor B. And then there's going to be one within treatment variance. And remember how we computed variances in the one-way ANOVA? We computed a mean square, right? Which is kind of like, what was it? Short for the mean squared differences, right? And that equals sum of squares divided by degrees of freedom. So we're going to be using that same basic formula here in the two-way ANOVA. The important thing to remember is keeping track of which sum of squares and degrees of freedom we're talking about or computing. So there's going to be a lot of different numbers, kind of like with the one-way ANOVA. We'll have a table of numbers and figures and calculations, and just keep track of which one's which. So when you're computing one F ratio, make sure you've got the correct sum of squares and degrees of freedom values. And this will make more sense in a minute when we do an example. Okay, so new example. Researchers investigating the relationship between anxiety and performance. It's been shown that the level of anxiety tends to improve the level of performance, but for very difficult tasks, increasing anxiety tends to lower the level of performance. So we will look at performance across 3 levels of anxiety and 2 levels of difficulty. I'm just going to pause here and make sure you guys understand there's 3 levels of anxiety and 2 levels of difficulty, but take note, there are 2 factors, right? So this is still a 2-factor or two-way ANOVA because there is the factor of anxiety and the factor of difficulty. Even though there are 3 levels of anxiety, anxiety itself is still just one factor. So test yourself, what would this design be in the ANOVA notation that we talked about at the very beginning of the lecture, right? How many numbers would there be and what would the numbers be? I'll give you a second. Remember, the number of numbers should correspond with the number of factors. And then what the numbers are should correspond with how many levels are in each factor. So this would be a 3x2 design. And so how many numbers are there? There are 2 numbers, right? The numbers happen to be a 3 and a 2. That corresponds with the levels of each factor. So there are 3 levels of the anxiety factor, 2 levels of the difficulty factor. Okay, so just a review there. How many cells or groups does a design have when we're making our matrix or table? How many cells or boxes should there be? Remember, that's also the same number of groups of participants that there are, and you get that by multiplying. So 3 times 2, 6. There are 6 separate groups. Okay, so our summary table, this should look kind of familiar, but there's some additional things. So we've got our sum of squares, degrees of freedom, mean squared, and F values here across the top. The difference is that our between treatments variability is broken down into three different things, right? Factor A, factor B, and the interaction of A and B. We still have the within treatments variance, which is also the error variance, and then total. And we're going to be filling in the relevant boxes up here. Okay, so the first thing, kind of like with our ANOVA, you kind of do the initial prep work or initial calculations. You have to start by finding the N, which is the overall sample size, the G, which is the overall sum of all of the scores, the T for each condition, and condition here is referring to each level of each factor. So let's take a minute and look at this table that I've got here. You've got anxiety level across the top. And remember, there are three levels: low, medium, and high. Along the left-hand side, you have task difficulty, and there are two levels: easy and difficult. And so 2 times 3 equals 6. There are 6 different boxes here. Each one lists the individual scores, then a mean for that condition, the t value, and a sum of squares. So you'll see each of the 6 have all of those. The t is the sum of scores for each condition. And so we would need to calculate that. And then across the at the end of the rows, you'll see there's also T and N for each level of the factors. So there's T for easy task difficulty, N for easy, T for difficult, N for difficult. And then same thing at the bottom of the columns. There's T and N for each level of anxiety. And then lastly, you've got your N and your G and your K. K is the total number of cells. So we would need to fill all of this information in as kind of the initial step of getting ready to do our ANOVA. And so now would be a good time to pause and maybe just on a scratch piece of paper, calculate for yourself these T's for each condition, T easy and N easy, and the T's and N's for the anxiety levels, and then overall N, G, and K. Make sure you fill in all of these question marks. On the next slide, you can check your work and make sure that you've done it correctly. So here's the same table, just reproduced in a slightly different format here. So I've filled in the T's. Here's T and N easy, T and N for difficult. Same thing, T's and N's for low, medium, and high anxiety. Here's our overall N and G. Oh, also sum of X squared. I didn't have that on the previous table, but that should be here. And then the only thing that's missing is K, and K is equal to 6. So now we're ready with those initial calculations to begin computing the values for this ANOVA summary table. Okay, so we will start with total, the sum of squares total and the degrees of freedom total, which we'll fill in down here at the bottom. So the sum of squares total, this formula should look familiar to you. You'll have these formulas to use on the exam, of course. It's the sum of X squared minus G squared over N. So again, the important or tricky thing is going to be just recognizing which formulas to use, making sure you put the right numbers in when you're plugging numbers into the formula, and then that you're putting them in the right place in the table. And so our sum of X squared is 860, our G from the previous slide, and you should maybe make a copy of this or put that in your notes, refer to it. It's going to be hard for me to keep flipping back and forth, but all of these numbers that you see here and on the subsequent slides are coming from this table. This is kind of our initial calculation table. So I compute sum of squares total, I get 380. The degrees of freedom total is the big N minus 1. So there's 30 minus 1 is 29. And so those values go down here under total, sum of squares, and degrees of freedom. Then let's do within. So the sum of squares and degrees of freedom for within treatments, or the error term. So the sum of squares for within, if you remember, this again should look familiar from our previous lecture on ANOVAs. It's the sum of the sum of squares for each treatment. And so these are the sum of squares for each treatment condition, again, coming from that initial ANOVA calculation table. And you're simply going to add them up and you get 120. Same thing with the degrees of freedom. You're going to add up the degrees of freedom for each treatment condition and you get 24. Another way to calculate for degrees of freedom for the within treatments is to take n minus k, the total sample size minus the number of groups. So that's 30 minus 6. You'll see that's also equal to 24. So that's a good way to check yourself for this degrees of freedom within value. And I put those values that I've computed into the table. So 120 and 24 go right here in the within treatments row. Now we'll do between, and we're going to start, before we break it down, we're going to start with the total between treatments, sum of squares and degrees of freedom. And if you recall, there are two ways you can calculate this, and I suggest doing both ways, making sure you come up with the same answer. That way you know your math and your plugging in of the numbers is all correct. So the simplest way to calculate sum of squares for the between treatment variance is to take sum of squares total minus sum of squares within. So 380 minus 120 equals 260. Very straightforward. The computational formula is the sum of t squared over n minus g squared over n. So you would take each t value for each condition, square it, divided by the n of that condition. You'd add those all up and then subtract g squared over n. So here, so the t squared for the first box or group or condition is 15. So 15 squared over the n for that same box or group or condition is 5. So 15 squared over 5, and then add that to the next t and end. 25 squared over 5, 50, and so on and so on. So here I'm adding up all the t squareds over n, and then I'm subtracting g squared divided by big N. When you do those computations, you get 260, which perfect. We want it to match what we computed up here, 260. We can put that in the box, sum of squares for between treatments, 260. Now we need the degrees of freedom. Same thing, you can take the total minus the within. So 29 minus 24 is 5. You can also, for degrees of freedom between, take the number of cells minus 1, or k minus 1. So 6 minus 1 is 5. And again, these are two different ways to compute the same thing. I recommend doing both of these just to make sure that you are getting the same answer. Put it in the ANOVA summary table. Okay, so now you remember we had two stages, right? Stage one was doing all of this, breaking down the total variance into the between treatments variance and the within treatment variance. And then stage two is going to be partitioning that between treatment variability into the main effects and interactions. So we will, let's see, compute a sum of squares for factor A, the main effect of factor A, sum of squares for main effects of factor B, and the sum of squares for the interaction. The interaction notation is just A by B. What that indicates is the interaction term. And we're going to use these to determine the numerators for our 3F ratios. Remember, bonus question here, what is the denominator for the 3F ratios? It's the within treatments variance. So we've already got the denominator, it's here, right? And we can use that to calculate our denominator for all 3F ratios. We're going to use these sum of squares, we're going to compute those, and those are going to become the numerators of our 3F ratios. Okay, so factor A. This is the first one we're going to do. In our example, factor A defines the rows, so we'll evaluate the mean difference between the rows. Out here at the end of the row, we call these marginal means. Down here also at the bottom of the column, these are called marginal values. Inside the table these are called cells. And so we're going to evaluate the differences between the rows, right? Here, this row is representing easy task, and this row is representing difficult tasks. And so for sum of squares A, you're going to take the sum of t squared over n for each row minus g squared over n. So t squared, if you look, for row 1 is 90 and the n is 15. So here we've got 90 squared over 15. And then here's t squared for the second row and n for the second row. We're going to add those together. So the sum sign comes from minus g of 120 squared divided by 30. That equals, if you do the math, 120. The degrees of freedom is the number of levels of A, or the number of rows in this case, minus 1. Just remember, you'll have these formulas, but degrees of freedom should always be some value minus 1. So in this case, we have 2 rows, 2 minus 1 is 1. So we can put that in our table down here, sum of squares for factor A, which is the level of difficulty. Sum squares is 120, degrees of freedom is 1. We're going to do the same exact thing for factor B. In our example, factor B defines the columns. So we're going to evaluate the mean difference between columns. Down here at the bottom are marginal values. So in our example, remember we're looking at columns. So sum of squares B is going to be the sum of t squared over n for each column minus g squared over n. So t squared divided by n for column 1. I'll go back. Here's our t value for column 1, or low anxiety, is 20. The n is 10. So that's where I'm getting these numbers, 20 and 10. 20 squared divided by 10. The next column, t is 40 squared divided by 10, the n is 10. And the third column, t and n values. So again, the tricky part, there's no super complicated math on these ANOVAs. The most complicated thing is choosing the formulas, keeping track of everything that you need to fill in these tables, and make sure that you're pulling the right number from your preparatory or initial table for all of these sum of squares calculations. Again, subtract g squared over n, which is exactly the same as the factor A sum of squares that we just did. When you do the math, you get 80. For degrees of freedom, just like with A, we're going to take the number of levels of B, or the number of columns, minus 1. And so there are 3 columns, right? Low, medium, and high anxiety. So 3 minus 1 is 2. And then we'll just put those values down here in our ANOVA summary table. You can see we're getting close to being done. Now, the interaction, which is A times B or A by B, you would say. And remember, the interaction is the leftover between treatments variance that is not due to the main effects of factor A and B. So between treatments variance, we've already calculated the sum of squares and degrees of freedom. You can break up the between treatment variance into main effect of factor A, main effect of factor B, and the interaction. The interaction is whatever between treatment variance is remaining after you take out these two main effect variances. And so because that's true, we can just do some very basic subtraction, okay? So sum of squares for the interaction of A and B equals sum of squares between, this between treatment sum of squares here, minus A minus B, because this is just the leftovers. So we'll take 260 minus 120 minus 80, and you get 60. For degrees of freedom, you can do the exact same thing. The degrees of freedom equals the between treatment degrees of freedom, 5, minus degrees of freedom for A, 1, minus degrees of freedom for B, 2, and you would get 2. Another way you can do this and check your math is to take the degrees of freedom of A times the degrees of freedom of B. And so 1 times 2 is 2. The same answer, right? The answer, degrees of freedom for the interaction, is 2, no matter how you calculate it. Okay, so now we need to turn our sum of squares into variances in order to calculate our F ratios. So remember, our F ratios are going to come from these mean square figures, and the mean square figures are going to come from sum of squares and degrees of freedom. So for mean squared within, we're going to take sum of squared within divided by degrees of freedom within. Again, just taking it straight from the table. Mean squared within, which is going to go right here, comes from 120 divided by 24. 120 divided by 24, and that equals 5. Recall that the within squares, or excuse me, the mean squares for the within variance is going to be the denominator for all 3 F ratios. I'm going to plug in the mean squared within into the ANOVA table. So I just computed this, going to put it in our summary table there. Now we're going to look and try to find the mean squared numerators for our 3 F ratios. So mean squared A is simply sum of squares A divided by degrees of freedom for A. Same with B, mean squares equals sum of squares divided by degrees of freedom. Same thing for the interaction term. So you should pick up on a pattern here, right? We're going to be taking 120 divided by 1 to get the mean squared for A, 80 divided by 2, and 60 divided by 2. And here I've done these calculations going down. So mean squared of A time for the interaction is 60 divided by 2. That equals 30. So pretty easy computations. And then plug your answers or the values that you compute back into the summary table. Now all that's left is to compute our F values. Final step. Remember to use mean squared within, which is 5, as a denominator for each of our F ratios. And just to review, any variance within the groups cannot be due to the between group variance. So that's why we're using that within treatments mean squared for our denominator. So the F for A factor is mean of squares A divided by mean of squares within. And that's 120. That's coming from right here in the table. divided by 5, which equals 24. Same thing, F for B is mean squared divided by mean squared within. 40 divided by 5 is 8. And interaction term is exactly the same. So we fill in those values in our table. We have 24, 8, and 6. So now what? Our ANOVA summary table is complete. And recall, we're going to be doing 3 separate hypothesis tests, right? One hypothesis test for the main effects of factor A, a second hypothesis test for the main effect of factor B, and a third hypothesis test for the interaction. And so we need to look up our F critical values. We're going to look up those values in the table using our degrees of freedom for each test. Assume an alpha of 0.05. The degrees of freedom denominator will always be the same, right? Because for each of these F ratios, our denominator was the same, right? It was the within treatments mean squared. And so the degrees of freedom for that is 24. So when you're looking up your F critical in the table, the denominator for each of the F tests is going to be 24. The numerator, however, depends on your F value that you're looking up. So when we want to find F critical for A, factor A, we're going to use a numerator of 1 degree of freedom, right? When we're looking up in the table to find F critical for factor B, we're going to use degrees of freedom of 2, and same for the interaction. So looking at our table, remember we're going to need 2 values. We're going to need the degrees of freedom from the numerator, and then along the side here, degrees of freedom for the denominator. So the first one, factor A, degrees of freedom. Oh, I'm sorry. Yeah, degrees of freedom for the denominator is going to be 24. That's coming from this value right here, the within treatments degrees of freedom. And then factor A, the numerator degrees of freedom is 1. And so our F critical is 4.26. Remember the regular font, there's 2 values here in this box. The regular font is for alpha of 0.05, and the bold font and value is for an alpha of 0.01. So 4.26, I'm going to put that in our table here for F critical. Now let's do our F critical for factor B. Again, the denominator degrees of freedom is still 24 for all 3 of these F critical values that we're looking up. In this case, the numerator degrees of freedom is 2. And so the F critical value right here that we find, looking up 2 and 24 degrees of freedom, is 3.1, or excuse me, 3.4. And I'll put that in the table. And then lastly, F critical for A times B is going to be exactly the same, right? Because it's 24 and 2 degrees of freedom. Same value for F critical, 3.4. Okay, now our results. Okay, so the main effect of difficulty here, difficulty was our A factor. So the way you would report that is F of A equals 24, and the degrees of freedom are 1 and 24. Our F critical for those degrees of freedom, we looked up in the table, was 4.26. So our F obtained is certainly greater than the F critical, and so we would reject the null hypothesis. For the main effect of anxiety, our F value we calculated is equal to 8. That was for degrees of freedom of 2 and 24. The F critical, when we looked it up, was 3.40. Again, our F value is greater than the F critical value, and so we would reject the null. And the interaction of difficulty and anxiety. Our F was 6, F critical was 3.4, and so again, we would reject the null. Let's look at that interaction. Remember I told you that maybe sometimes the clearest way to see an interaction is to graph it. And if there are parallel lines, there is no interaction. If the lines would eventually cross or they're not parallel, there is an interaction. And in this case, increased anxiety tends to improve performance, right? So let's break this down. On the x-axis, we have anxiety, 3 levels, low, medium, high. Our other factor is difficulty. And so we have one line for each level of difficulty, a blue line for easy, a red line for difficult. And then on the y-axis, we have our dependent variable, which is score, right? That's our performance data. And so looking at this, we see that increased anxiety, going from left to right, tends to improve performance. But when the task is difficult, which is the red line, increased anxiety decreases performance. So you see from low to medium, things are the same, right? A little bit more anxiety. So when you have low anxiety and you add a little bit of anxiety, your score goes up, whether the task is easy or difficult. But when you add increased anxiety to a high level, in an easy task, the score keeps going up quite a bit, right? Even more than this initial amount. But for a difficult task, an increase of anxiety now lowers the score. And so the level of anxiety is influenced by or depends on the level of difficulty. And so there, we would say there's an interaction here. Time for me to embed my random question for your extra credit, since we're looking at red and blue here. What is my favorite color? I'm going to say blue. So not red, yellow, green, purple, orange. My favorite color is blue. So go on D2L, answer that quiz question for a super easy extra credit point. Okay, now effect sizes. Hopefully you might have guessed that we were going to have effect sizes, right? Just like t-tests, just like the one-way ANOVA, we can measure effect size. So if we get a significant result and we reject a hypothesis, whether we reject all of them or one of them, we would then want to look at effect size to see just how significantly different the means or the groups or the levels are. And we can use eta squared for that with ANOVAs. It measures the percentage of variability in the total sample that is explained by treatment effects. And when I say variability in the total sample, you should think of sum of squares total. And that's explained by treatment effects, you should think of sum of squares between. The problem is that since we have sum of squares between broken down into sum of squares for A and for B and for the interaction of A by B, we need to remove variability accounted for by the other sources that we are not trying to look at. So in other words, when we measure the effect size of the main effect of A, we can't just look at the sum of squares between. We can't look at all the treatment effects. We just want to know the treatment effects of A by itself. And so when we're computing eta, we need to take out sum of squares B and sum of squares for the interaction and just look at sum of squares A. So just keep that in mind from a conceptual standpoint when we go and look at these formulas, and that'll make a little bit more sense to you. So eta squared, or effect size for the A factor, is going to be sum of squares A divided by sum of squares total minus sum of squares B and sum of squares for the interaction, right? Because again, we're interested in the effect size for just the A piece. And so we need to take our the percentage or proportion of variability that is explained by A. So the proportion of the total variability explained by A only, taking out any variability explained by B and the interaction of A and B. If you do some algebra, you'll see that that is equal to sum of squares A over sum of squares A plus sum of squares within. All right, and you'll notice for eta squared B and eta squared interaction, A by B, it's the exact same formula, just subbing out the various pieces. So when we're looking at B, we want to subtract A in the interaction. When we're looking at eta squared, or effect size for the interaction, we want to take out A and B. So we do these, plug in some numbers and do the calculations. Eta squared for A is 120 divided by 120 plus 120. So sum of squares A divided by sum of squares A plus sum of squares within happens to all be 120. When you do the math, you get 0.5. And how we would interpret that is 50% of the variability in performance is due to difficulty. Remember, because A was our difficulty factor. When you do compute eta squared for B, you plug in the numbers and you get 80 and 80 plus 120. You do the math, you get 0.4. The interpretation is that 40% of the variability in performance is due to anxiety. And then the interaction effect. And you get 0.33, so 33.3% of the variability in performance is due to the interaction between difficulty and anxiety. Lastly, just to go over, there are assumptions that you need to check when you're doing a factorial ANOVA. This is nothing new. The observations within each sample must be independent, just like a lot of the other assumptions of hypothesis tests that we've done. The populations from each of the samples are the populations that from let me try this again. The populations from which each of the samples are selected must be normal. And the populations must also have equal variances. This is the homogeneity of variance that we've talked about before. And in this case, it can be tested with the Levene's test. And you'll probably, I think, definitely learn about that, or at least see where that comes from in SPSS in the lab lecture. Okay, some learning checks here. If a two-factor analysis of variance produces a statistically significant interaction, then you can conclude what? So I'll give you a minute to read through these and see if you can determine the correct answer. And this is a great example of a question you'll probably see on the exam. So when you know there's a significant interaction, what do you know about main effects? The answer is D. The significance of the main effect is not related to the significance of the interaction. So you don't necessarily know if either the main effects are significant, if neither of them, if both of them, you don't know anything, right? Because main effects and interaction effects are completely independent of each other. You can have one without the other. So when you know that there is a statistically significant interaction, you don't know anything about the main effects. They may be significant, they may not be. If the mean and variance are computed for each sample in an independent measures two-factor experiment, then which of the following types of sample data will tend to produce larger F ratios for the two-factor ANOVA? So do you want large or small differences between sample means? And do you want large or small sample variances? Which is going to give you the larger F value? And hopefully this is kind of a review. It's the same in a two-factor ANOVA as it is in a one-way ANOVA. Since the F ratio is the variance between divided by the variance within, then from like a mathematical standpoint, you want a large numerator, large variance between, and a small denominator or small variance within the samples. So we want a large difference between samples, which would give us a large numerator, and a small sample variance, which would give us a small within group variance, which would give us a small denominator. That would lead to a larger number divided by a smaller number, which would be a larger F ratio. True or false? Two separate single-factor ANOVAs provide exactly the same information that is obtained from a two-factor analysis of variance. So this is asking, what's the point of doing a two-factor ANOVA, right? If you've got two independent variables like anxiety and level of difficulty, why can't you just do two ANOVAs? Do one ANOVA for anxiety, do one ANOVA for level of difficulty. Wouldn't you get the same information that you would get if you did a two-factor ANOVA? True or false? The answer here is false, and this is an important key concept. Main effects in a two-factor ANOVA are identical to the results of two one-way ANOVAs, but the benefit or bonus of the two-factor ANOVA is that you get interaction results also. So in my example where you have anxiety level and task difficulty, you could do two separate one-way ANOVAs and you'd get the same results to tell you whether or not anxiety and task difficulty make any difference. But you wouldn't get the interaction. And so that's where the two-way ANOVA is important. Okay, true, false. A disadvantage of combining two factors in an experiment is that you cannot determine how either factor would affect participants' scores if it were examined in an experiment by itself. So is that a disadvantage of doing two factors in one experiment? And the answer here is false. The two-factor ANOVA allows you to determine the effect of one variable controlling for the effect of the other. So controlling for just means that we're examining the effect of one variable on the dependent variable independently, as if the other independent variable or factor did not exist. So remember in one of our examples, I think it was level of difficulty and anxiety. When you're computing main effects for, let's say, level of difficulty, you are determining the effect of level of difficulty while controlling for the level of anxiety. That means you're doing computations as if anxiety didn't even exist in your experiment. And so there's no downside. You do get to see that effect by itself. Okay, That's it for chapter 13, two-way ANOVAs. Do the practice problems, go into MindTap, do those practice problems. I'll make sure that there's some posted on D2L. Your textbook has some too, so no shortage of practice that you can do. Let me know if you have questions. Maybe watch the lecture video again or refresh, review in the textbook and MindTap, and reach out if there are any remaining questions. Please ask specific questions. If you ask a question that I've answered in this lecture or that's in your textbook, I'm probably not going to answer. Um, so I do expect you to watch this video and to read the textbook. If you're still confused about something, ask me specifically what that is and we'll work it out. All right. Take care, everybody. Thanks for watching.